share the snacks in Poles. We all have 3 plates.
Oh, Lina, should I take away my computer? We could compress it here a little bit.
No, I'll be sitting behind.
Everyone's here? No.
You will have it.
So, don't worry about the time.
No, come on. So I mean, I thought that I have a very strict limit of 45 minutes or so, but then Stan told me that you are all interested in details and that you all like pain. So I was adapting the slides, you know, because I thought I'd make this very light presentation after dinner, which is swallow. But now I was added some pain for the experts. And
no pain, no gain.
Thank you.
no, yeah. So let's see how it goes.
Are you recording for it?
Yeah.
Yes.
We lost the input. You see, so this is the dangerous part. Is it coming back?
Yeah.
Yes. Please.
Yes. Yeah.
Yes. Okay. Yeah. So we should not allow the play to stay without input for too long because then it wants to go to sleep.
We have to do that once in a couple of minutes.
And I think I also can teach it not to do this, but you know,
You don't have to do that now.
yeah, exactly.
That's fine. It's a driver issue. We know
That's right. What do I say?
it. Is that yours?
Okay, we can start. So, everyone, welcome to New Theory. So, today our guest is Falk Hassler, and we've been talking about generalized geometry and five fractions.
Yes. Okay.
Welcome.
Okay, yes. So, hey everyone, so it's very, very nice to be here. I really appreciate that I got this invitation and that I could come. And yes, today I heard that there are some absolute experts on the topic of alpha prime corrections. So when I'm doing things too simple or so, just stop me and ask me more detailed questions, because you all know, right? It can be very, very technical in the certain aspects of the calculations. And so, of course, it's very hard to communicate all the technical details in the talk. So that's why what I try to do is I have half of the talk, which is more an overview and give some of the conceptual ideas. And especially for the not extreme experts, this might be interesting just to get some ideas what's going on. And then I have the second part of the talk where I want to go more with you into depth. And in particular, you know, we have this list here of papers. And perhaps the last one is the most important one. So which is actually doing all the calculations, and from there I also copied some of the equations to the slides, and I just want to highlight for you some points in the calculation where we were struggling and where I think some interesting things also from a conceptual point of view. Okay, good. So that's the plan for today, and please, whenever you have a question, stop me. Let's make it a little bit more like a dialogue. So, and I'm very happy to give further. Okay. Please. Why? Oh, wait. So now it's doing something here. Let me move my mouse here. Yes. Okay. Good. Very good. So let me give you just the general statement of the problem. You of course know that the Einstein-Hilbert action in gravity is not renormalizable beyond 2 dimensions, right? In 2 dimensions it is. So that's why string theory is so cool. But usually, you know, we live in 4 dimensions. And so that's why the problem is that usually people only see it as an effective field theory. And we heard a lot about this in the talk yesterday already. And so that what does this mean? Of course, we start with the Einstein-Hilbert term, and I just neglected measure contributions here. And then, you know, we get an infinite tower of higher derivative corrections. And usually it's very hard to find them. I mean, one could go to nature and try to measure them. Or what we usually like to do is we like to have another tool which helps us actually predict these coefficients in front of all these different terms. And of course, you all drank the Kool-Aid. So what we have is one way to calculate these coefficients is the string theory. And of course, you know that the higher derivative corrections in string theory usually come in 2 forms. So on the one hand, in string theory, we have the genus expansion of the world sheet. so which is actually controlled by the string coupling, GS. And then on the other hand, so on every world sheet, so for example, this thing here is the simplest you can have. This would be a 4-punctured sphere because, of course, you have conformal symmetry. You can deform this shape here and you would just get a sphere with 4 punctures. And then, of course, what you can do is you can calculate loop corrections on your world sheet theory. And so these loop corrections on your world sheet theory, so they are usually coming with alpha prime corrections. And then, of course, you also have GS corrections. So usually the idea is that GS corrections are even more complicated than alpha prime corrections. So what I will do, probably also most of you are doing at the moment, so we will just focus here on alpha prime corrections. But in principle, it would be also nice to say something about GS corrections. Okay, so and to make this a little bit more clear, so what's going on is so we can happen or we can check what happens at the leading order. And of course, in general, we have a superstring theory, but here what we will do is we will focus on the NS sector mostly. And the reason why we do this is because so it's shared by most of the interesting superstring theory. So it's in the heterotic theory, it's in the type 2 theory, and it's also in the bosonic theory. And in principle, you know, most of the things we are doing is just valid for bosonic because we don't care very much about supersymmetry at this point. But in principle, of course, we can also learn something about heterotic strip. So how does it look like? So most of you, nearly all of you have seen this low energy effective action here. So there's 3 terms here. And the interesting thing is, in principle, you know, when you want to write down something which has just 2 derivatives and which contains the metric, the B field and the dilaton, and then of course, which transforms nicely under diffeomorphisms, you can only write these 2 terms. So there is not much more you can write. So that means in principle, you would have 3 different coefficients here going to this general scheme I was explaining to you from the first slide, which you have to fix. And of course, all you know that this is a 4 here and this is a 1/12. And one way people usually argue that these coefficients are fixed is by supersymmetry. So in principle, just diffeomorphisms and gauge transformations will not fix them, but then you have some additional symmetries which fix them. And then you can go to the next order, so you can allow for 4 derivatives, and for 4 derivatives, so you can already write much more, and you know this, so in principle, you can actually check that when we have 2 derivatives, 3 coefficients, and so when we have 4 derivatives, so we have 8 coefficients. When we would have 6 derivatives, we would have already 60 coefficients. And so this counting already takes into account field definitions, which you can do. Because of course, you know, usually you can decide what is your metric and what is your B field, and you could redefine them. And so there is some nice work, for example, by Barussi. You all know this. So, and he was very careful checking, first of all, what are all the terms you can write down. And so this here, for example, at 4 derivatives, this was already done by Akarditzek and Mitseyev. So I think they had 12, but then they were showing that they can remove some of them by field redefinitions. There is just a minimal basis or set of terms which you can add. But you see, so the problem here is that the number of these terms grows very, very quickly. So that means in principle, when you are have even more derivatives, 8 or what do I know, 10, so it's nearly impossible to fix all these coefficients. So that's the problem which we are all dealing with. So that means too many terms, and in particularly, of course, what you can do is you can try to calculate these coefficients directly from string theory using scattering amplitudes or beta functions, as we learned yesterday. But also this becomes nearly impossible when you have more than 8 derivatives. So there is nothing really known. So the question is, can we have a better approach to try at least to understand what is going on there? And can we at least try to cut down this number of additional coefficients so that we might get some idea where this is going to? And one idea to do this is that we want to leverage some symmetry to decrease the possible number of terms. So this is a very, very general idea. And so far we have just looked at diffeomorphisms and gauge transformation, But of course, I was also telling you that in general, you can do supersymmetry or something else. So supersymmetry is very nice, but as far as I understand, one problem with supersymmetry is that in particular, when you have a lot of supersymmetry, it's very hard actually to have it manifest and really work with it. So there are some superspace approaches, but they only work with low numbers of supersymmetry. When you have more supersymmetry, it's very hard even to do superspace. So that means getting these kind of higher derivative corrections from supersymmetry is hard. So people are trying to do this, but it's hard. So what I want to follow, and so this is actually what I think also you are following, I want to use another symmetry, which is more towards generalized geometry, the T-duality, and falls into this broad form of ideas. So, and this is actually, for me, it's manifesting as a generalization of Lorentz symmetry. And this is actually what I want to look at today. And so for the experts, so at the moment, you know, what I really want to do is, before I will get new results and tell you something new, I just want to better understand what exists there. And the most, I would say, and we can discuss about this, but so the most sophisticated way of getting higher derivative corrections at the moment using generalized geometry is what is called the generalized Bergshoeff-de Roo identification. So this is just a tool which actually is a little bit like black magic, you know. So you have your prescription, you turn the crank, and you get corrections, and they, as also Linus and Stanislav were showing, they work to certain orders. But it's not, at least for me, it's not completely clear why this works. So, and one thing I really want to tell you today about is that we can get a better understanding why this works. And then we even might get a better understanding about the shortcomings of these approaches and see whether we can extend them, right? So, and all this, of course, is related to generalizing the Lorentz symmetry. Okay. So what are we doing here? So this is all what you know. So when we want to do generalized geometry, so we have to introduce an object which is a generalized frame, which can be actually parameterized by the normal frame and the B field. And so then we find that this object here is not just invariant under the normal symmetries which we would have. So that means, or it transforms in a nice way diffeomorphisms and gauge transformations, but we even get this ODE symmetry here, where we also introduce our eta metric and our generalized metric. And I don't have to say much here about this because you are already expert in these topics. So what happens is when we do this, so we of course now have a new way of capturing our degrees of freedom in our theory. So we now have introduced our generalized frame, and then of course we have to study the symmetries which this generalized frame has. And so to do this, what we are using is we are using the generalized Lie derivative here, and this just implements the symmetries we already know. So we implement diffeomorphisms, which tells us that we have a theory of gravity, and we implement gauge transformations for our B field. And this can be not just done for the bosonic string, it could be also done for the type 2 strings or even for M theory, where we would get a more complicated group, not ODD, but some exception. And then the second thing is because we have a frame, so we also have to introduce something which is similar to Lorentz symmetry for a normal frame. And this is exactly what people usually call generalized or double Lorentz transformation. In principle, you should call them generalized because they appear also for other dualities. And so this is some kind of artifact also from the transformation of fermions. So this is the idea. And then you know what you want to do, and so we have also seen this in Stan's talk so very nicely. You want to find natural objects which transform nicely under these symmetries. And of course, the well-known candidates are the generalized fluxes, so FABC, which just can be written down as a derivative of our generalized frame, and then the same guy here, which is working with the dilaton. So that's the nice covariant object. But of course, you also know from the talk yesterday that while they are transforming nice under the generalized Lie derivative, so they are much more complicated when it comes to this generalized Lorentz transformation. So that means there are some nice building blocks, but they are not the final answer. Good. But when we have this, we can write down at least two derivatives, so we can write down an action, which actually can be written just in terms of one quantity, which has a very nice geometric interpretation, and this is just the generalized Ricci scalar, and we can write it down in terms of our S here and just derivatives, and so this generalized metric here, which can be also made constant. So that means all the information about our physical theory are actually encoded in these two objects here. And why is this nice? It's nice because this, of course, looks like the Einstein-Hilbert action. So, and this thing here is square root of minus g, and this is just the Ricci scalar which we would have there. Yes.
So why is there only a three-form flux and not higher order fluxes?
So this is that two derivatives all you can write down, right? So you can write down this quantity here. So, and there are no higher order fluxes. Of course, what you could do is you could combine several of these blocks here, but you see you also have to contract all the indices, and you can only have two of them, because otherwise you have more than two derivatives. And so this is just a two derivative action. So this is the nice thing. So this is really what you can write down. And you see also that this is fixed up to one coefficient. So you don't have three coefficients anymore, but imposing this extended symmetry, and this is something natural in physics, right? So the more symmetry you have, the more constrained you are. So you have already solved this problem with the three coefficients. And then, of course, so because this is the only invariant you can write down, it would be now nice to do something similar at higher order in derivatives. And so now, I think so far this was mostly a repetition for you because you already know this. So now I want to tell you something a little bit new, because I want to present you a way to formalize this kind of idea and also to apply it to higher derivative theories, for example. And when you think about what we were doing so far is we had a certain input, and our input were just symmetries. So we know that we have generalized isomorphisms, and then we had something like generalized Lorentz symmetry. So these are the inputs. And then we were saying we are actually looking for a way to find invariance. And I'm just giving you the final result here, even without showing the full form. And so then we can use this invariance to write down an action. So this is the idea. So now this would be nice when we could do this in more general settings. So that means we have some symmetries, and we will see later on exactly what these symmetries are. So we will always have generalized isomorphisms, because we always have B-field transformations into homomorphisms. But then, we might swap these generalized Lorentz transformations for something more complicated. And then again, we have this machine which gives us the invariance, and we in principle could write down. So, and of course, then it depends on the symmetry which we are choosing, how much this action is restricted. I mean, ideally, we want to restrict it as much as possible. On the other hand, we still want to match it to string theory. So that means, in principle, what we are doing is we are playing a little bit guessing here, because we are saying that string theory might have implemented in it a more complicated symmetry, which we cannot see at the moment. So, but we want to figure out the symmetry. And here, ODDs seem to be fine, at least at the leading order. But then, as we have seen in Linus and Stan's work, there are some problems with ODD. So it might be something else. Okay, but this is the idea. How does it work? So in principle, what we need to do is we need to find invariance, and we need to find quantities which transform in a nice and covariant way under certain symmetries we impose. And this is one of the main problems actually in generalized geometry, as Stan was explaining in his talk, because there, for example, there is even a problem with the Riemann tensor. So we have a problem to write down a nice covariant Riemann tensor. And I want to try to explain to you a little bit where this comes from and how we can resolve it. So when you want to write down covariant objects, usually your biggest problem is that your normal partial derivative is not transforming covariantly. So this spoils everything. So, but of course from GR, you know that there is an easy trick to solve it. You just introduce a covariant derivative, and you add a spin connection and you add an affine connection, so you have two kinds of connections here because you have two different indices. So each one transforming under a different symmetry. So the M here is generalized diffeomorphisms and the B here generalized Lorentz transformations. So actually these two connections, you also know this, are not independent, but you usually impose that your connections are compatible with the frame. And the reason why is you want to push the frame through the covariant derivative, right? And when you can do this, you can write down everything in curved indices or flat indices, does not matter. And by imposing this equation here, you actually relate the affine connection with the spin connection. So you can choose whether one you want to use. I usually, and I'm not sure how it's with you, but I usually like flat indices. So I will write down everything in flat indices. But when you like the opposite, you can always rewrite it. There is no problem. Okay, and this thing you can always do, and you can also do it in generalized geometry. And then, of course, you can ask what are well-defined notions of curvature and torsion in the setup. And you have learned this in your GR course. So when I tell this my students, I say, okay, you take your two covariant derivatives, you commute them, apply them on a vector, and then what you will get is you will get your Riemann tensor and you will get your torsion tensor, and everything is fine. When you think about this, that this works, and I was never thinking about it, but I now understand it, that this works is a miracle. So it's not guaranteed, because what you have here on this side, you have an expression which is clearly covariant by construction. So that means this whole side here also has to be clearly covariant. But the problem is, who guarantees you that this term on its own is covariant and this term on its own is covariant? Nobody. So in GR, it's a very nice coincidence that both terms on its own are covariant, but in general, it does not have to happen. And this is actually the problem in generalized geometry. So we will find, of course, that the whole thing here will be covariant, but not the individual terms. So that means from this point of view, we cannot really define torsion in such a way. And so we also don't really know how to define torsion. So that's a problem. And there is a nice way out, so which I now want to explain to you, which is this Polacek-Siegel construction. And so this can be also seen for, this is just a footnote for mathematicians. Fortunately, there are no real mathematicians here, but they understand the symplectic reduction of Courant algebras. So, okay, good. So what is this thing actually doing? So this thing is actually solving the problem that, as we also heard in the talk yesterday, that it's sometimes very, very easy to find quantities which transform covariant under one of the two symmetries we have. So it's very easy to write down something which transforms covariantly under generalized diffeomorphisms, and we have seen these guys as ABC. So they transform nice there. But then we have a problem with generalized diffeomorphisms. So on the other hand, we can go to curved indices. Then everything is manifestly covariant, which means invariant, right? Because we don't have flat indices under generalized, Lorentz transformation. But then, of course, we have to fight with generalized diffeomorphisms. You see, we can try to rotate it as we want. We always have problems to implement both symmetries at the same time. So that means when you think about it, it's a little bit like they don't like each other and they don't want to get merged together. So, okay. But you see, this Polacek-Siegel thing actually gives you a nice way out, and so it answers some of the questions Stanislav was raising during his talk. So the first thing is that what he was saying is completely right. We don't really know how to write down a complete nice Riemann tensor in double field theory. Because when you try to do this, you will always find that some projections of this Riemann tensor will not transform in the way they should. So, and this is what people were doing. People were first trying to write down the normal Riemann tensor. It was not working at all. Then they were adding some additional terms, and they could get it working a little bit better, but they always had certain components which were not transforming in the right way. So, and this is a problem when you want to get a nice geometric point of view on this whole story. But what you can show actually with this Polacek-Siegel construction is you can actually find the underlying reason why this does not work. And the reason why it does not work is that in generalized geometry, you cannot just work with the spin connection. So it will not work. And the reason therefore is because you might have heard that generalized geometry actually has gauge symmetries for gauge symmetries. So what you can write down is you can write down a trivial gauge transformation. And so this trivial gauge, I'm not sure, do you guys know this? Do I have to show you how this works? Or you know this, right? Okay, good.
Oh, we meant like you have to show.
Oh, you have to show. Okay, good. So what you always can do is, so you can have, for example, your generalized frame. And so you do generalized derivative on this generalized frame. And then you have a parameter here, right? So this is usually what you can do. And so this parameter here is a sin I, which, you know, in principle contains information about my diffeomorphisms and my Beaver transformations. But what I can do is I can choose this psi I as dp. And when I will do this thing will not change at all. And you can easily plug it into the equation, and then you see that the section condition actually will kill all the terms and you will get 0. So that means you have a gauge transformation, which is non-trivial because this thing is not 0, but will not act on your fields. So that means in principle, this can be understood as a gauge symmetry for your gauge symmetry. This is called gauge for gauge. And this is very, very common in generalized geometry at all. When you take more complicated groups, you will actually get another symmetry for this one. So you get a whole tower, and this is gauge for gauge symmetry.
But you can do the same in supergravity, right? So
you can do, and supergravity.
Normally we don't worry about that.
Exactly. So in supergravity, it's exactly the same thing. But you know, in supergravity, you never really try to describe it in a nice geometric way, right? You never really try to construct curvatures which are compatible with all the symmetry of supergravity. So this is what generalized geometry is doing. I mean, in supergravity, you still use the normal Riemann tensor,
right?
But it does not care about the B field, right? You cannot really unify. But you are right, of course. This thing comes from the B field, right? You see this because the B field you can shift by a trivial gauge transformation. Yeah. This is something which is built in. And also from what you are saying, and this is a good point, when you have more than a B field, when you have higher forms, this becomes more complicated. And this is exactly what happens in exceptional field theory. And you know, people actually know this kind of thing. So this is what's also sometimes called ghost for ghost structure, because when people do this in BV, so which is the, I have no clue about BV, but as far as I understand, which is the really sophisticated framework to treat these kind of symmetries. So it's represented by ghost fields, and then you have ghosts for ghosts, and you get this kind of.
So you got it right.
Okay, good, very good. So this is the idea, you see, and for this effect, and this is actually what we only understood, and this was, I think, I'm not sure. I mean, Siegel, you know, Siegel knows a lot of things, but it's very hard to decode it. So that's why I cannot say that Siegel did not know this, but at least we were never getting this out of Siegel's work. I mean, we were just playing around. And we were seeing that we need some additional connections in generalized geometry, but then we were trying to do the same for exceptional generalized geometry, and we were not getting one extra, but we were getting a whole tower. And then we understood actually that they come in exactly the right representations you also will find for this gauge for gauge. So you see, this is the first observation. When you really want to find something and when you really want to write down something which transforms nice and covariantly, you have to get rid of certain concepts you were taking for very natural and generalized geometry, and you have to extend them. And the first thing is you need an additional connection actually for the symmetry here. And you can even see this. So just since we have a little bit of time, you see that this object here does not have an index, right? So this is in a way in a trivial representation. And you also see that this thing does not have a capital A index. So it only has alpha indices, and it's always antisymmetric in the alpha indices. So, and you see here, this A index actually comes from this sign. And then here, the missing index, you could make a dot here. I can use this, right? Because it's a black hole. So the dot here comes just from this object, which does not have a dot. the hard full dot here as well, because there is no index. And then, you know, you would get, for exceptional groups, you would get even more, which come exactly in the right representations. So this is the first thing you have to change. And then the other nice thing is, so now you see you have some additional fields in your theory, but still, you know, I have to tell you how you use these additional fields to now write down a nice expression for a curvature tensor and a torsion tensor. And the thing is actually what you are doing is a very, very old trick. So the first thing you have to remember is that usually torsion is not a problem in generalized geometry. Because there's a very simple trick you can write down torsion, because what you know is that the generalized derivative is already covariant. And the reason why it's covariant is because it closes, right? Its closure makes it covariant. But when you look at the generalized derivative, you see that it's written in terms of partial derivatives. So that means it's surprising that it's covariant because it's not manifestly covariant. So, but then of course you can say, okay, but I can also write it with covariant derivatives. I mean, then it's super covariant. It's not different covariant. I mean, you can be only covariant or not. So that means you have a generalized derivative, which is written with partial derivatives, and you have a generalized derivative, which is written with covariant derivatives. And then of course you can take the difference between them, and you will get the torsion. So this is the way you always can define torsion, and by definition, so this torsion tensor will be covariant. So that's why torsion is simple. And then what we see, the normal torsion tensor in normal geometry is antisymmetric with respect to the first two indices. But in generalized geometry, you know that the generalized derivative has 3 terms instead of 2 terms, right? Which makes this antisymmetric with respect to all 3 indices. And then you can exactly see where the problem starts, because what I was showing you on the first slide will construct something which is antisymmetric just with respect to the first 2 indices. And this is exactly where this problem comes from. So that means this Polacek-Siegel construction actually tells me we can always calculate torsion, but we cannot calculate curvature. And the trick now here is to say, okay, can we try to just go to a higher dimensional space where we just need to calculate torsion, and then can we try to use this torsion to get from the torsion, and curvature on a lower dimensional space? So that's the idea. And so when Ondra Hulik would be here, so you could ask him whether mathematicians have done this before, and they have, and this is Cartan geometry. In Cartan geometry, this is exactly the idea. So Cartan geometry goes to a higher space, and there are different approaches. And again, I'm not an expert in Cartan geometry, but one approach to Cartan geometry is you go to a space in higher dimensions where you just trivialize your tangent bundle. And so when you have a trivialized tangent bundle, so you know that you never will have curvature. So you can always write down, because the curvature, you know, tells you the violation of your tangent bundle to be trivial. So that means you can write down a connection which only has torsion, no curvature. And this is sometimes also called Taylor parallel connection. And then you can calculate this torsion, and you will find that this torsion contains the torsion and the curvature of your physical space. So this is the idea behind Cartan geometry. And so what Polacek and Siegel was doing is they were doing exactly the same for generalized geometry. And this is actually the way you can construct nice torsion and curvature tensors. And what you will find, and this is also not surprising because you now have 2 fields, you will find that you will find the Riemann tensor for this object here. But, okay, let's see. So we can recover. Yes, we can recover. Okay. So you will find the Riemann tensor for this object here, but this Riemann tensor will also contain this object here. And this object transforms in a highly non-trivial way, and together these transformations will make it covariant. But then you need another Riemann tensor for this object here, and you get exactly this hierarchy of curvatures. Yes.
So in this way, you will not get when you reduce bank from your megaspace, you will not get something covariant of the Riemann tensor. You will just get the same one, but it is somehow packaged in this higher dimensional torsion.
Exactly. So the problem is, and so what you're saying is an extremely good point. So the problem is you have introduced now new fields, which is usually a dangerous thing because we know our degrees of freedom. So that means these new fields have to be pure gauge. And you know usually how this works because so in normal double fields theory, this thing here, or at least certain components of it, can be expressed as derivatives of the frame, right? So that means you can integrate them out and you still keep the same number of degrees of freedom. And this is actually what is very important when you do higher derivative corrections. We will also see how this works. So, but you are right, when you are removing these fields, so you get something very complicated looking, and of course you lose all the nice symmetric structure. And so, again, I'm not an expert on superspace, so Linus is the expert here, so he has to correct me, but as far as I understand, superspace is actually quite similar, because you add a lot of auxiliary fields, you get a nice structure where symmetries are linearly realized. But then, of course, when you integrate out all your auxiliary fields, you get something very complicated, and it's just messy.
Falk, can you comment? So you say that the Polacek and Siegel construction, which apparently proliferate a lot of fields to
yes.
Get
this. And I will show you in a second how this works.
And you're saying that mathematically this can be understood with the Cartan geometry, but you had a previous comment 10 minutes ago about symplectic reduction of Courant's algebra.
Yes.
Can you comment a little bit about the relation?
I mean, this is something also probably not to bore everybody else here. So first of all, we should ask Ondra tonight because he knows much more about these kind of things. But I can show you that these things are a little bit related to symplectic reductions because, you know, for symplectic reductions, for example, you know that you need a momentum map, right? Because in the symplectic reduction, you usually have the problem that your space-time dimension has to be even. Otherwise, you cannot have a symplectic structure. But then when you have a U1 symmetry, for example, and you would reduce, you would just take away one direction. So you would go from something even dimensional to something odd dimensional. So what you are doing is you are introducing your momentum map, which is the second direction in a way, and then you can reduce. And so here you will see exactly the same structure. So that means mathematicians usually, you know, they see Courant algebroids coming from what is called PQ manifolds. So these are graded manifolds, which have some symplectic structure. And then they can do a reduction on the symplectic structure, and they will get exactly the same thing, which we get with Polacek-Siegel. The problem with the math literature is, I mean, I was thinking a lot about these kind of things, and I was trying to extract something from the math literature. It's very hard because they don't work in indices and they have very abstract statements. So that means when you really want to calculate explicit expressions, I mean, at the end in coordinates for your object, it's very hard to get this from the math literature. Okay, but let me go on because I don't want to waste too much time on this. So only to say a little bit how this works. So you have this extended space, and this extended space is now just, again, O, D plus N, D plus N. So this is actually where everything lives. And then, of course, what you want to have at the end of the day is you just want to have objects which live in ODD. And you want to have this GS, so which is the structure group, and this might be your Lorentz transformation or whatever you want to implement. So this is the whole thing. And so this Polacek-Siegel construction is actually making a decomposition, and we will see this in much more detail. And so what it actually tells us is we don't really are interested in this whole space here, but there is a subspace where exactly these objects live. And so this is normally called as G Polacek-Siegel, and this then contains the structure. And only this data here is in some sense needed. So when you have this data, and I will show you more explicitly how this works, you just seek your factory and it will give you invariance and it will give you nice quantities. So that's the idea. Coming back to Cartan geometry, to show you a little bit how this works in Cartan geometry. So what you have in Cartan geometry, you have your Cartan connection. And what I'm doing as a physicist, I write it in indices, so mathematicians will hate me for this. But you see, you can always bring it into this form, and you see that your Cartan connection actually contains your spin connection and your frame. So that's the thing. And this is the extended space, right? So you have the extended space now. The headed indices are indices on an extended space. And then you can just write down something which is called a Cartan curvature. And so when you would write it down in indices again, you would see that it looks exactly like the torsion of this extended space. And then you see when you decompose this object here with respect to these indices here, so where alpha is the index for the Lorentz group, which you have, and A is the normal space-time index for translations, and you can of course then decompose the results accordingly, and you will find the torsion and you find the rematch. This is Cartan geometry in its symbols form. So now you can do this in generalized geometry. And so the nice thing what you are seeing is you have this kind of upper triangular form here, and you just keep this in generalized geometry. And then of course you have to ask, okay, what is the most natural frame on the extended space which I can write down with this upper triangular form, still being compatible with ODD. And then when you do this, you find you cannot just add a spin connection, but you can also add this rho field. So it just comes from representation theory from ODD. So it has to be there. And then what you are doing is you are writing down the generalized part-time curvature, and it's exactly kind of taking this equation and write it down, and here you write it with Dorfman bracket, and this is exactly that. I mean, I was just writing this for the mathematicians, so they like the Dorfman bracket and so on, but it's exactly the same idea here. You just write down your generalized fluxes on the megaspace, which is the torsion when you have no curvature. And then what you will find is you will find all these different components, which now contain your normal torsion tensor and your generalized torsion tensors and all the torsion components.
So the deep data term is somehow contained in the Dorfman bracket?
Yes, it's contained in the Dorfman bracket. And you know, so the one problem with generalized geometry is that we cannot really write down generalized forms. So, I mean, when mathematicians always ask me, these things look very different, then I say, but only because you never write them in indices. When you would write them in indices, you would see that this becomes the Lie bracket, and it becomes a twisted Lie bracket. It's exactly the same thing. So this is generalized geometry. So, but now you see, so now I was making some advertisement for a nice mathematical gadget. But of course, now I have to tell you how we get higher derivative corrections from this, because this is what we were starting with. And actually, the whole problem in doing this is to choose this symmetry group, which now should be larger than a normal double Lorentz, and to choose what we want to have for G Polacek-Siegel. Because when we fix these two, we are already done, and we can just generate nice covariant objects, and we can check whether they correspond to our action or whatever. So this is really the point. And of course, you know, this is in general very hard, because we have to guess, or we have to find a way to get these kind of things. So we just a priori impose them, and then we go through the full machinery and we check whether we find something which is realized in string theory. So there is no obvious way from the string, at least at the moment, not for me, to really see what you should choose. You just should be clever in choosing. So how does it work? So the objectives is actually what we do is, so we first choose these two, and then we have all these additional fields, so which have the interpretation of connections. And then of course we have to get rid of these additional fields because there are no physical degrees of freedom. But from normal geometry, we know how we do this, right? So what we can do, one thing what we can do is gauge fixing, because some of them might be pure gauge, so we just gauge fix them and they vanish. And the other thing, of course, what we can do is torsion constraints, right? We use this in normal GR to get rid of the spin connection. So we have these two kinds of things. And so this is also very, very similar, but I don't will comment more on this, to the BV formalism, because the BV formalism actually gives you a very powerful method to find physical degrees of freedom and gauge degrees of freedom. And it really tells you how to do these kind of things. But we were doing the poor man's version. We are just trying to get rid of everything additional we have and just keeping the physical degrees of freedom for the moment. And so then what really happens is we can fix all these connections just in terms of the generalized frame and derivatives on it. So this is what we want to do. And then, of course, we have to choose our invariants, and we want to fix these kind of symmetries in such a way that they're so strong that we only get very, very few invariants. Of course, you know, we could make this symmetries very weak, and then we have the same problem as we had before. We can write millions of terms. But when we make them strong, then we can only write very few terms. And when we choose them in the right way, hopefully these few terms are exactly the terms which are realized. So that's the idea. And in a way, this is nice because so this is the same what we are doing in general relativity. So it's very geometric. Okay, so and what I will show you is actually, so now coming back to the Bergshoeff-de Roo procedure, you know, I was trying to do, together with my PhD student, to find a choice here for these kind of groups such that we get exactly Bergshoeff-de Roo. So this was the idea. And these groups are very large, so one probably could make them a little bit smaller, which one wants to do according to Linus and Stan's results, because you know that Bergshoeff-de Roo cannot capture certain corrections which are in string theory. So that means these symmetries at the moment seem to be too restrictive. So one might try to relax them. But okay, so this is something we could discuss later. So for the moment, I can just choose them in this way. And I will now show you how to get from this choice the standard results from Bergshoeff-de Roo. Okay, so I have to warn you, so this was more the introductory part, so which gives the idea. Now it will get more painful because we will look at some explicit implementations. Okay, the implementation idea here is actually that we first have to look at this Polacek-Siegel, because so this is the most important group. And so this group will contain our physical degrees of freedom, and it will contain all the additional connections which we want to get rid of. So we better understand what this Polacek-Siegel is. And then when we have understood this Polacek-Siegel, we will understand the structure group, G structure, which is a subgroup of Polacek-Siegel. Okay, so what is this Polacek-Siegel? So the Polacek-Siegel, what we were saying is that, I was saying this earlier, so I was saying, where was I saying this? I was saying this here. So we want to always implement ODD into this, right? Because ODD is really the thing we are interested in. So that means when we write down the Polacek-Siegel, is we want to have ODD generators. And so these are actually ODD generators, you know, and these are the full generators of Polacek-Siegel. And you know, what you are doing, and you might not be familiar with this notation, but this thing here is actually some kind of a level decomposition of this group. So you also now introduce this R generator. So you have your ODD generators, and you have an R generator with one gauge index, and so this index is actually the index of GS, so the second group which we have, and then also with one ODD index, and you have the quantity which has two gauge indexes. So this is the most general generator just for this Polacek-Siegel. So this is the way you would decompose it. And then you see, so this Polacek-Siegel is an O, D plus P, D plus Q group, so that means it should satisfy this very simple commutator here, where you have now an eta metric. And so this eta metric has now the normal eta metric you know from double field theory, and then it has a kappa metric, which is new, and this kappa metric in some way describes your additional gauge symmetry, which you do. And actually, you see this kappa metric is the most valuable player in this whole game because, as we will see later on, it contains all the information about the deformation. So when you know kappa, you know everything.
Can you comment? I mean, so I don't have any intuition. But I mean, I thought from Standard's talk yesterday that P and Q were more or less always the same.
I was not doing any extensions.
Right, but why would can you give some intuition why P and Q are two independent?
P and Q are two independent because, you know, so this splitting here, so in some way, you know, this is already a guess, but it's a very natural guess because it comes from the left and the right moving sector of the string. Right. And so there's the bosonic string, where left moving and right moving sector are democratic. So
is it like the heterodic?
Exactly. And
heterodic.
Okay.
The heterodic. Okay.
Which you also could describe. So there would be not, and there would be a difference between them. So that's the reason why you have that. And this is a very good point, actually. You know, when we go on, we will usually only look at one sector because the other sector is just a copy of it. So either it's trivial or it's the full copy. So that means we only will look at this, but we come to this in a second. Okay, so this is the thing for Polacek-Siegel. So we have this very nice structure, and the only thing we don't really know at the moment is this kappa here. So this is something we have to fix. And then, so besides this kappa, there is also some additional information because we also have our G structure group, which has to be a subgroup of G Polacek-Siegel, and this can be generated in different ways. So one way to generate it is to use these R generators here, and we can just write down an R alpha. And the R alpha in some ways, so this is a very implicit definition. It contains the structure groups from G Polacek-Siegel, and it will generate exactly the same structure groups when you look at the commutators here of this R thing. Because you know the R commutator R alpha beta with R gamma delta, you can of course get from this commutator here. And then when you just take an R alpha with an R beta, the generator, you can use them, you use the commutators here, you will see exactly that you get the right thing. Okay, so but of course at the moment, so what we really don't know is this kappa here, and we don't know really the structure coefficients. When you know both of them, you have a perfect definition of G Polacek. Do we agree on this point? Very good. Hopefully. So otherwise we can also discuss it later on. So but these are in some sense the definition or the quantities we have to define, and of course they are related to our structure. So that's why we look at the structure group next. And you see, for the structure group now, to define it, so what we actually want to do is we want to define it recursively. And so there is a motivation for this recursive definition. And so the motivation for this recursive definition is we want to remove all our connection parts. And what you will figure out is that you can always, when you fix a certain structure group, you can start to remove some connection parts. But then you get new connection parts, which you cannot remove. Then you have to make the structure group a little bit bigger, and you will again be able to remove the ones you want to remove, but you will generate new connection which you still cannot remove. And you see this already from this very simple fact that when you look at the connection, so you have omega alpha b and rho alpha beta, you see, so this is exactly the G structure index. So when you make G structure bigger, the connection becomes bigger and there are more components you have. So that means what you are doing is you are trying to find a way of just having a recursive way to making G structure bigger in the same way that you can fix all the components of the connection, and then you make it bigger again and again and again. And this is in a way natural because you know in the Bergshoeff-de Roo identification, you know that you have to send this group to infinity. So you have to have an infinite dimensional group, but there, of course, you don't know anything about the structure of the group. What we learn here is we learn more about the structure of the group. Okay, so this is the first thing, so that's why it's recursive. And then, of course, you know, we have these generators from the last slide as seeds. And we want to have this on the left side and on the right side, right? So we don't want to have any mixed indices, but we just want to have the left and the right side. So that means I choose this generator's tau here. It has an overbar and an underbar, so this is left and this is right. And both of them are the same, so we just look at the left part. And what we start is we start just with T alpha 1, and you see, so this is the K generator. And so when you remember that K is generating ODD from the last slide, you know exactly that K bar, so overbar and overbar will just generate OD. So, and this is of course one of the Lorentz generators, right? So that means alpha 1, so the first step in our iteration, will just give us a double Lorentz group, which is natural, and so which is also what Polacek and Siegel were doing. So they were just saying we're geometrizing the Lorentz group, and that's it. But then, you know, when you want to do identifications, you will also hit these two generators here, which you would not be able to identify. So that means you have to make this larger. You also want to keep the R generators, which you need in your identification. So what you are doing is you are writing down R alpha 1 A and R alpha 1 beta 1. So, but then you have a problem because now you have some new generators, which are alpha 2. So you also have to implement the R alpha 2A and so on and so forth. And you do this at the next level. And this will go on for forever in principle. I mean, you can truncate it because you can show that all of these themselves are subgroups. So they're close and they are nice when you choose them in the right way. But then, you know, you would hit at some point the problem that you cannot really identify the connections anymore. So They would become interdimensional. So another nice thing is that when we do the calculation explicitly, we were saying that we are seeing that this grading here in a way which you introduce, and it's not really a grading. So the algebraic structure is more a filtration, but so you still have the structure alpha 1, 2, and so on. So this will also count in some way number of derivatives. So the higher you go in derivatives, so the more important it is that you also go here higher in this kind of expansion. But you see, this is just a practical way of identifying this group in such a way that you can remove all the additional connections. So this is the way you would know. Okay, are there questions at this point? No. Good, great. So that means what we see is we have an exponential growth of generators. And so although that in principle, what I tell you is that this can be truncated at every order, so we don't have to make it infinite dimensional. So this is nice, we can keep it finite dimensional. Okay, so, but now what I have to tell you is I was introducing for you this kind of new generators, T alpha, or tau alpha, and I have to tell you how they really work, what kind of algebra they are forming, because it's not obvious immediately from this kind of discussion. So, of course, what we want to do is we want that they generate our key structure group, so which at the leading order is just double Lorentz, but then we get more than double Lorentz. So that means in principle we have to calculate the structure coefficients. But you see, this is not so hard because we can express them in terms of k. This R here and this R here, and when we go one slide back again, we know that they just satisfy this commutator relations. So we can really calculate everything explicitly. And when we do this, and when we sit down and do this, we will actually see that these guys here will just, so this is just a scaling factor, because we are always free to choose certain scaling, that they can be expressed completely in terms of this eta. So that means this eta, again, is the only thing we really need to know. But when you remember, so this eta here had the normal ODD eta in it, and it had the kappa. And so that means everything is just fixed in terms of the kappa. When you have specified kappa, you have specified everything. So you know everything. So that means the last thing what we have to do is we have to fix kappa. And we have to find a way to consistently fix kappa. And what we're saying, of course, we want to understand kappa as something like a killing metric. So it should be the natural metric for our structure group, because although one additional thing what you see from the construction is that when you lower the last index here with the kappa, everything should be nice and completely antisymmetric. So that means kappa should be an invariant under the action of the structure. And what you actually can do is, and this is nice, you can actually find a recursive definition of the kappa, where you just say you take your etas, you take two etas, you split the indices of this two eta, and this will give you another kappa. And this is the only slightly tricky thing here, what you have to understand. You have to understand how to evaluate this equation here. So, and I can show you, so here I start with alpha 1, and you see that alpha 1 always decomposes into two indices, A and B. Here I have alpha 2 decomposes in two indices. So that means what you do is you always take an index and split it into two parts. And then, of course, here you see that I have an alpha 1 here, so I can split it again further. So it's a little bit like a game of index splitting. And you know, when you want to keep this thing is you should call these indices here alpha 0. You call them alpha 0, you just have a normal Latin index, which is your target space index, and then you can always split indices. And so this is exactly how this recursive thing here works. So when I want to have, for example, kappa alpha 1 beta 1, so I go into this definition, I know that this here splits into an alpha 0 or an A0 and a B0. This is a C0 and a D0. And then I plug it in here and I see that I just get the normal Newton metric from the altitude theory. And when you do this, you will see exactly that, for example, this kappa here is exactly given by this expression. And then you do it again and again and again, and it works perfectly fine. It works recursively. You can specify the whole structure from this recursive relation. So what I've now done is I've constructed for you a G Polacek-Siegel and a G structure. And what I'm claiming, and this is what we will check, is that with this thing here, we only have one parameter, so which we see here. This parameter will be exactly the A parameter or the B parameter in the generalized Bergshoeff-de Roo construction. And when I choose this G structure and G Polacek-Siegel, I get everything which is in generalized Bergshoeff-de Roo. So this is my claim. So this in some sense is the input. And now we just have to turn the crank, and I have to show you a little bit more how you turn the crank, and we will get all the transformations and everything from there. Okay. So what I was telling you is that we have to do two things, right? So we have to do torsion constraints and we have to do gauge fixing. So that's really the thing. And you see, torsion constraints actually, so can be very simply done from the Polacek-Siegel construction. So because what we have is we have this generalized Cartan curvature on our extended space. And so we have said that some components of it are the torsion. So that's a little bit tricky to identify them, but you can do this. So, and we just want to set these components to 0. And we have imposed a torsion constraint. So, and you see, so then what we have to do is this torsion constraint has to be powerful enough to just fix our omega and our rho here. So, and then we are done. So for the future, this omega and this rho, conceptually, they are two different things. So this is the spin connection, and this is the higher connection. But you know, here for this, they are just connections. So that's why we call them A, just not to have to distinguish between them. So, okay. And then, you know, when we have the structure, so what we will say is we will impose this torsion constraint here. So we will all put all the mixed chirality components of torsion to be 0. So this is a consistent thing. You can show that this condition also under transformation works perfectly fine. And then I also say that I want to remove all the chiral components of this kind of thing here by a gauge fixing. So, and when I do this, so I have my torsion constraints and I have my gauge fixing constraints. And in the rest of this talk, I will just show you that when you impose these constraints, you will exactly get generalized. So that's the idea. Are there questions? So this is just now, we will just implement these kind of ideas.
So the kappa that you introduced, it was fixed uniquely by the choice.
Yes, so it's fixed uniquely by the choice up to an overall coefficient, and the overall coefficient is this G minus. So you have one overall coefficient on the left side and one overall coefficient on the right side. The problem with the kappa is actually because this generalized Bergshoeff-de Roo takes this huge group as the structure group, and as G Polacek-Siegel, this group is simple, and there is no other choice. When you make this group smaller, then of course you have more freedom to choose the kappa. So that means what they have is they have an extremely constraining symmetry, which I think, as far as I understand, it's too strong, because you in principle don't need this to just do what you want to do, because you want to fix all the unphysical stuff. So of course you can do this with this huge thing, but it's not required. Okay, that's a very good question. Okay, good. So then, okay, let's start with the torsion constraints, right? Let's see actually that we get something more to generalized Bergshoeff-de Roo. So when we do torsion constraints, so, and I spare you the detail, I just want to show you a little bit how this works. Is when we set these components here to 0, what we actually find is that we can identify these components of the A here by just calculating this F here. So, and you see, so the thing is, we are working with a megaspace, and you might complain about this, but we are using some index-free notation for certain expressions. And the reason I can explain to you, so it's twofold actually. The problem with the megaspace is it's really huge. So that means in principle, like a good physicist, you could start to just have megaspace indices, but they are usually horrible to work with because they are so huge. So that's why what people usually do is they use this bracket notation here. And so, for example, also this Z, what you're seeing is, so this is a way to write down a generalized Lie derivative in an index-free notation. And it looks a little bit like quantum mechanics, right? So what you are doing is, so you have bras and cats, and you can go from index to index-free notation. There is also, I mean, in principle, one do not have to do this. So sometimes also my collaborators get mad at me why I'm doing this. The reason is for ODD, you could even work without it. So when you like indices, you can always write down these things in terms of full indices, and it's fine. When you want to do exceptional groups, it gets crazy. You don't want to do this because you run out of letters in the alphabet for different kind of types of indices you need. And so what we are doing, we are trying to write these things in a very general way so that in principle you could also do this for the exceptional groups. It's not completely clear what it means, but just to excuse myself for this weird notation, when you have calculated, so these will be the heterotic fluxes on the extended space. So it's just a generalized Lie derivative, it's just this curvature, or this torsion, better to say, on the extended space. Generalized fluxes on the extended space, so that's why it's called F. And you know, of course, these generalized fluxes on the extended space, just to give you an idea. And when you look at the formulas, I can help you. So they would be something like F, A, B, C. So this is the thing. But what I'm doing is I always contract with generators because, you know, I want to stay index free. And then this is what is my FA here. Just to explain this thing. So this is the FA here. And here, you know, I actually give you the explicit way using the parameterization of our frame to calculate this. So that's why you find the A here. And the physical frame actually only appears in this F here, where you have just a generalized fluxes for the physical frame. So this is nice. The physical frame never appears naked.
So how should I understand the kits as the generators and the bras as?
No. So what you actually want to do is, you see, so what I was writing down for you, for example, was writing down for you KAB, right? And I was telling you that this is a generator, right? But of course, as a generator, it should act on a vector. So how is this thing acting on a vector? It acts on a vector by putting a C here and a D here. So this thing is actually what I would call KABCD. So then this would be a matrix. So this would be a matrix. And then of course here I can choose which generator I want to have. So this is the way of this Ra and ket notation. And so what you actually do is you build highest weight states. So this is actually, so you know when you're talking this tensor hierarchy things here, so this would be an R1 representation, for example. So this is where it comes from. So that means you can write down everything in indices, but you see here, I will already gain 2 more indices. And then of course I have to contract all these indices. And I don't want to do this. I want to write down things which look like a Maurer-Katana form or like an adjoint action. And when I would write down all the indices here, it would be crazy, right? So that's why I want to suppress these indices. And only, you know, at the end when I need 1, or when I have a derivative. So derivative is always hard to write it like this because it has to act on something. So that's why the derivative comes with an index, and that's just the way we do it. And I mean, one could discuss about it, but so far for our calculation, this has been proven as quite useful because you can also implement it in Mathematica. Because what it is, what you have to do to calculate these things, it's just normal ordering. So you have to implement normal ordering, which is easy, and then you can calculate all these kind of expressions directly in Mathematica, and you don't have to do it by hand. So that's another way why we're doing this, because otherwise it just becomes painful. But you see, I mean, I understand when people like to do it in indices, it can be rewritten completely in indices, and the paper explains how it can be rewritten in indices. So
what is the meaning of your upper index to the first row?
Oh, this is the best. This is a very good question. I should have said this. So this actually counts the number of derivatives in this thing. So this is exactly the way you see that it counts the number of derivatives. And you see the nice thing, you also see this F here, it only has 1 derivative. So that means in one step you can only grow by 1 derivative. But then, you know, so you collect all the derivatives in these fields here, and you get more and more derivatives. And then when you collapse everything, this is the way you actually get your higher derivatives. That's a perfect thing. And this is actually how you do the identification. You go on step for step for step for step. Very good. So you see, and then you have this let here, so which is actually, I'm not sure how much you know generalized geometry, but when you write down the generalized derivative, you write it down with the y tensor or with the z tensor. And this is the operator version of the z tensor. It's very funny because this is also mathematically the split Casimir operator. So, which has a very nice mathematical meaning. So, mathematicians also could understand this equation. But okay, so this is just a generalized derivative written in a fancy way. Good. But I mean, of course, what we need to know here is we need to know this A here, so all our degrees of freedom. And the A actually here for us is just written down because it's a group element. It's an element of G Polacek-Siegel. And it's actually everything in G Polacek-Siegel, which is not the generalized frame. So it's a coset element. And the coset representative we take is actually written down in this way. So because of chirality, you can only get off powers here. And then we were putting coefficients in here, C3, C5, and so on and so forth. And these coefficients are very nice because they actually capture that you can choose different parameterizations for the A. So, and these coefficients are the only things you can do for your parameterizations. That means when I have fixed these C coefficients, I have singled out parameterization. And for you, this is very important because I know that you were dealing a lot with field redefinitions. So choosing different C's for us is just choosing different field redefinitions. So this is the freedom we have. And remarkably, what we will find is that you have to choose your C right. When you choose your C right, a huge number of terms is canceling. And so you have to find a field basis where things look remarkably simple. So that's the power here. And this is the way how we deal with field redefinitions. Yeah, so that's everything. And when we do this, so we can actually fix all of them by torsion constraints. This is fine. So then there is one more thing I have to tell you. So, and this is something actually we learned, which is called collapsing towers. So this is what we came up with, and I will try to explain it. Because when you look at this identification, you see a problem. We were describing our G Polacek-Siegel and our G structure group in terms of these taus, right? So these taus we understand completely fine. But when you look at these equations here, you will find that you will get this R generator here, which I have introduced. So, and I can show it to you again. This generator here, this will also appear. And this is a huge problem because, or it's not a huge problem, but it causes a lot of headache because it appears at the same order as the field you want to identify. So that means to identify what you have to bring it on the other side. Then you are not dealing actually with your tau generator anymore, but with your tau plus R generator. And this actually introduces a new generator, which we now call T. So this is actually the generator you encounter in the identification. And this explains why you have all this weirdness of recursion and doing it again and again and again in the generalized Bergshoeff-de Roo identification, because they have exactly the same problem, but they don't see it because they cannot really decompose these indices. So what you have is you see that actually you not only have the tau generator, but you have the T alpha generator as well for the identification. When you have a finite basis of generators, this is not a problem, because of course all of you understand that this is just a similarity transformation. I have just to do a matrix, and the identification is a little bit more complicated. I have to change my basis. So that means there is a matrix S here, which actually connects these two guys here. And then, you know, because I'm not working with tau generators, I take all my quantities like my kappa from my tau generator, I dress it with S, and then I get the same quantity which I would get for my other generator. So this is the thing you are doing. And the problem actually, what happens is that when the quantity in terms of these tau generators is nice, this is what I can show you. So for example, when you have a quantity which is psi, and I call it will alpha, tau alpha. So I can have this quantity here, and then I can have the same quantity here, psi alpha, t alpha. So it's the same generator, but now you know what can happen is, usually what happens is that my psi trill only has an alpha 1 component. While, so this is something, while all the other components, alpha 2, alpha 3, and so on, so they are all 0. Which is nice, because I only have very, very little information at the bottom of the hierarchy of generators which I have. But now, when you look at this thing here, which comes from this transformation, what you actually will find is that this psi alpha 1 is even the same as this one, but then it will start to have a psi alpha 2, and it will go on forever. It will have a psi alpha, and it will go on forever. So that means what you are doing in some sense, and that's why we are calling collapsing a tower, you are trying to build a whole tower of different values, just starting from a seed value, which would be here alpha twiddle alpha 1. But then you get this whole tower. And then, of course, when you have two of these quantities, and when you contract their indices, you contract everything which is in the tower. So that means you have the whole tower, you connect it with another tower, so what I know, 3 alpha 1 twiddle, but you connect all of them here, and you collapse them. And of course, only the information which is relevant is this information here, but depending on how large the tower is, you can get quite some large numbers because you are adding up all these kind of quantities. So this is the problem with collapsing the towers. And actually, you know, when you make this kind of group infinite dimensional, so you have a problem because you are summing up an infinite number of numbers, non-vanishing numbers, and they usually diverge. So that means you have to find a way how you regularize the sum, and there are actually different ways how you can do this. And this will be important because you can choose any way you want to regularize it, you can keep it finite, you can calculate it. But in principle, what you will find is, and we'll show you later, the gauge transformation which recede after your gauge fixing will in general not close when you not do it to the right side. So there is a very particular way you have to regularize the sum to really make the residual gauge transformations close. And I think this is a very important aspect you don't see in the original Bergshoeff-de Roo identification, and it is coming from a very innocent fact that you actually have to change the generators here, which you see. So it seems to be very innocent, but it has quite far-reaching consequences. And I would be interested when any of you have some physical intuition why this is required. I would be very interested to hear it, or whether there might be even a way to get around it, because when you could get around it, you get a much, much cleaner and simpler structure. I will show you later. So this is in some sense, which costs us quite some time before we really understood how to use this property. Okay, so then we have this, you know, and then we can just do the solution for the torsion constraints. And now there are equations which you might be more familiar with, not in this way of writing them, but perhaps from other publications as well. So what we now have, we always have this twiddled versions here from the identification. And so we also have the untwiddled versions. And what happens is always that on the left side of the identification, on this side, so you have a twiddled version, and on the right side, you have an untwiddled version. And then you have to collapse the tower to convert them into each other. And sometimes you have to make this more often. So here, for example, here you only have to do it once. But then you see for this guy, you now have things here which are, so I mean, you have to collapse the tower here, and then you have to collapse the tower again to make this a twiddled version. So you have to do it again and again and again and again. And this is exactly the reason why this Bergshoeff-de Roo identification also has to be done again and again and again and again. The nice thing what you can see here is you can see more structure because you can now have all the intermediate results with the gauge indices, which in Bergshoeff-de Roo you cannot do, generalized Bergshoeff-de Roo, because you never have expressions with naked gauge indices. So the gauge indices are always contracted. But here, of course, we understand the structure, so we can always write these things down. And of course, the first identification, this is probably not surprising, it's just the F. So this is the first order identification. What I find interesting, perhaps you can tell me more about, is when I do the second order identification, I find, for example, this expression, and I think so this is exactly your generalized Riemann tensor, non-covariant generalized Riemann tensor, which I think you identified as a nice quantity to write down certain expressions in the action. And here, you know, in a way it appears very naturally just from this identification at this level. So you can do this, and you were going, I think, to third order or so, but you can do it to arbitrary higher orders. And the nice thing is you can put it in Mathematica and just making Mathematica spit out more and more of them. So there is no really problem in just going to.
Okay, can I ask?
Sure.
Back to this slide. How many of these any tools you will have? Like,
yes.
How many options for indices?
Yes. So this is a great thing. So this again comes exactly from your generators. because remember, so we have a generator. No, this one. Let me make some space for access to it here. There. So remember what we already have is we have this A here, and then we have an A index here, and so we have a beta index here, and we have a tau beta. So this A index here is A or alpha, so there are two possibilities here. And so this tau index, so this of course decomposes into a K, an R alpha A, and an R alpha beta. So these are the options. And then of course, you know, so this is usually what we call R1, because it has one alpha index, and this is what we call alpha index. And this is always the way we identify. And then of course, you know, these index structures can become more complicated, because again, they have to be decomposed. So this is how we get it. And here, these are the only contributions, but then for higher, you get more, and we have written that down. Okay, good. So, and then the last thing, so what we have to do is gauge fixing. So, and gauge fixing is, so we have the objective that we want to preserve this choice here under gauge transformation. Because, you know, usually gauge transformation would lead to some non-vanishing entries here, but of course we don't want to allow these gauge transformations because we have already gauge fixed. So that means what we have to do is now we write down the expansion of the gauge parameter, which is this psi here, and we know that the expansion of the gauge parameter, and this is very abstract, but I think it gives the idea, will give the A here. And for the A, we know that we are not allowed to have any chiral components, so they should be 0, these chiral components. So where we can have something is for the transformation of the E here. And so then we exactly know how to choose this side here. And this dot dot dots are all lower contributions, which we have already calculated. It always works like this. You calculate something, and then in the next order, you only see a few new additional things, and you can fix everything. And again, you see the problem here is, again, we have tau, T alpha here, so we have to collapse towers. So this happens in the same way here. And it in some way is exactly the same idea as the identification. You just go order for order and crank out all the kind of signs here. And this is also interesting in the Bergshoeff-de Roo identification, because there are two identifications here. And you can also see that this is the second identification. Here, the nice thing is that you have two different interpretations of these identifications. One is torsion constraints, the other one is gauge fixing. And so in principle, gauge fixing is more complicated than torsion constraint, because of course what you have to check at the end of the day is whether these new gauge transformations which survive, because you know here what happens is you can always choose your C alpha 1, but then all the others are fixed by this constraint. So you start, you can give something like an initial condition, and then everything else is fixed from the initial condition. But of course, you don't know whether this particular gauge transformation will close. So in principle, they cannot close. And then of course, you should keep all the other transformations as well. Or you might find that a larger subset might close for some kind of modifications. So this is an important point here, which is different from just a stupid identification in the torsion. So, okay, good. But what this allows us is it allows us to find the transformation for this A's. So for our connections, it allows us the transformation to find transformation for the E, and also it allows us to fix all the size that we can do pictures. So we are nearly done. So now at this point, I want to show you a nice result, because of course, since I was telling you we can calculate this transformation for the E here, we can of course also calculate the generalized control transformation, because this is exactly what should happen. And we actually have a very simple formula, so which looks to be a universal formula for generalized control transformations, and our generalized control transformations look just like this. So how do you read this formula? You just take your A and you just take a D on your parameter, and you restrict it to an even number of derivatives. And this minus CC is just chiral conjugation, because it always comes in here. And this is the formula for generalized Schwarz transformations. We verified it until order 4. So, and everything looks like this until order 4. And the only secret there is that you have to choose these coefficients in the right way. When you don't, it's a terrible mess. When you do, it's very nice. And so my PhD student, Achilles, actually, he's done this painful calculation. So what we find for C3, it is 1/3. So, and then I was telling him, look, Achilles, can you also do it to the 6th order? And he was spending, I mean, he was cursing a lot and so on, but he could do it. And it's something like 20 pages of calculation. But you see, what he found is he had to put C5 to 1/5. And then everything collapses and we still get the same equation. So it's quite remarkable. So that means, and this is not so, please don't excuse me, nobody will not excuse me. So, I mean, I think it's C2n plus 1 is something like 1/2n plus 1. And it will probably work for all orders. So, in a quite nice way. So, just choosing the right parameterization. Then you can think about, so what is the function? So, what is the parameterization? Okay, so this is interesting. So, you can write down this very simple formula for the generalized transformation. But, of course, with the thing that we still have to collapse the towers, and then we have to put in the identifications. And when you do this, and just to show you how this works, so here I was doing the first collapsing by just going from this A's here to twiddle quantities and applying this similarity transformation, and you already see that I gained some additional terms here with my S inverse here. But then, inside these terms, there are also still normal A's from the identification, so I have to do it again. So this is the first step. I have to do it a second time. And then when I do this, I get this thing here. And we had a lot of reason to party because, of course, in the beginning, we were not getting this thing here, but it's exactly the same what Baron and Marcus had. So, which is in some way a proof that we get exactly the same thing. So the interesting thing is when we look at the towers in different ways, these prefactors will change. Only the prefactors, the structure is the same, but the prefactors will change. And you see that then the transformation will not close. You have to have exactly these prefactors for things to close. So this is the important thing. So that means there is some way you have to be really careful about this business of collapsing towers. And so Marcus and Baron, they were using the right prescription to do it because they did not have very much choice, but here you have no choice. You see that this is actually restricting. And I would really like to better understand this aspect. So, I mean, I know how to make it work, but I'm not really knowing what is this, why is this thing singled out? Okay, and then just some remarks, because I think I already was speaking for much too long. Check, yes. So what we can do is, we have this prescription, of course, of collapsing the towers done in a particular way. So there are other ways of regularizing this thing which will not give you closing transformations. And then all the invariant action just follows very, very simply from the Polacek-Siegel thing, where we know that we can write down an invariant action on the megaspace, just two derivatives, we plug everything in, and it, of course, gives the right action, which they also have. So that means this is a little bit also in the flavor of what Linus and Stan were doing. Once you understand the transformation, the action in a way follows. I mean, it's not so hard anymore. It's just like a remark. Yeah, so I mean, the gauge fixing really breaks this hugely structure to just OD cross OD, which are now the modified Lorentz transformations. And yeah, so we have all these kind of things. There's only one invariant which we can write down. This gives exactly the right results. So for the future, of course, it would be very interesting to see whether we can push this further, whether there is a way of changing these groups to implement perhaps C++. So, and I mean, one thing I was telling this already to Linus, one thing we are trying to do with Martin's interval actually is to use more BV techniques of really seeing how to identify the physical degrees of freedom and the gauge degrees of freedom. And there seem to be some very nice relations between this idea of Polacek-Siegel and BV. And then what we hope to see is that we have more like a deformation kind of problem, which really tells us what are all the possible deformations we can switch on, and that we don't just have to choose GS so randomly, but that we really have a very systematic way to see what are all the admissible choices for GS and what kind of deformations. That's okay. So thank you very much. Sorry for talking too long, but you were telling me, right? So between 1 hour and 1.5, and so I think I'm still on the, okay, thank you very much. Sorry.
Also, more questions and comments? I wanted to ask about you were talking about this filter A and those factors of C3 and C5 are somehow related to filter definition.
Yes.
So can you say more about that? Because when I think about filter definition, there's always more options for
yes.
you can.
Yes. So that's interesting. So I can say a little bit more about it. So I mean, of course, you know, the way we are parameterizing our frame is already in a way constrained, right? Because so what we have is we have really this frame on the meta space. And so what we are saying is we have here our A, and then we have our physical frame E here. And so, of course, this A in principle could also have chiral components, right? But here we don't allow it to have any chiral components. We only want to have mixed chirality components. And the only way, in principle, that we can achieve this is when we put here this exponent, and then when we have A plus power of 3 and so on and so forth. So this is the way we can implement it. And you see that, of course, you could choose another parameterization. And then in principle, you know, so this tells you how omega and rho look, right? So it gives you some expression in terms of omega and rho. And of course, you could change these kinds of expressions. And then, of course, in principle, you could choose whatever you want here. So, and I mean, a lot of these ideas are actually from Dan Butter, which I now have to mention here, who thought a lot about these kind of things. And I think Dan Butter, for example, he has a parameterization where you can very easily see how the supergravity action arises. So by doing a different parameterization. I mean, for us, we wanted to find a parameterization where you see the connection to Bergshoeff-de Roo. But so then has this other parameterization which works very well with the supergravity action. But then, of course, you could just compare these two frames in these two different parameterizations and can identify the parameterization and have a picture. So here, you know, I think it's not the most general thing you can write down, but with our constraints on chirality and so on, I think this is all we can write down. And it seems to work for us.
That's
Sure. So, do I understand correctly that essentially the only freedom that you have in this construction is how you choose the groups that you start with?
Yes.
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 Structure. That's all the freedom is almost
That's all the freedom. But of course, you know, when you think about more careful, it's actually a lot of freedom because these groups are infinite dimensional in general. These groups are huge. So, I mean, one might think that it's only something very and very simple, but on the other hand, these are huge groups. Yeah, this is actually the nice thing about this approach because once you have done it, it's very methodical. You're turning the brain, and I mean, it can be still hard, but in principle, it can be done on a computer. And yes. I mean, of course, one thing that would be nice is, you know, whether you really find this kind of, whether you can find motivations of choosing them from string theory. And from string theory, you know, because in principle, they should be there. But I don't know, so there might be one thing which we wanted to do is we want to study, for example, Western models where you know the full power of orthogram correction. And then you might try to check your results because, you know, even, I mean, we hope that we can find successfully some way in this thing. So by modifying it, I mean, as you were saying, probably you cannot break it down to ODD anymore. So there will be perhaps something more complicated. But you see, even when you would find successfully, then there is very little you can do to check something else, right? So you would try to go to special points in your moduli space and still try to see whether you can achieve this to higher order.
But can you say at what order what's the lower order that you freedom?
This is deformation. I mean, at the moment, I cannot tell you. So because I've not done this deformation theory calculation, but the deformation theory calculation tells you exactly order for order what are the allowed deformations of this algebraic structure. So in each deformation you find would be a new parameter, which you could use. So that means what you would expect is that at 6 derivative at 8 derivative level, right? So always depends a little bit on how you count, right? So six derivative for the Green-Force transformation would be 8 derivatives in the actions. There is a new parameter. So this is one, and I mean this is one of the tests we really would like to do as soon as possible, because this is just a formation parameter, and up to this order, I think it's still possible to write down the algebra and everything in a more general. I mean, here you are very restricted. You will not use this. I mean, I was telling you there is something more relaxed, which is this Maxwell infinity algebra, which is a sub-algebra of this. So it's a sub-algebra of this, but which contains all the structure you need from the BV construction. So, and you would try to deform Maxwell infinity, and you would check whether it meets.
Yeah, at least it sounds like that's just an algebraic problem.
It's linear algebra. So you are solving linear equations. You have quite large matrices, but it's completely. I mean, it's like the algebra homology. It's the algebra homology. What are you doing? And you can do it. You can do it in the computer. And I think you need a supercomputer. You just do it on another computer. It might need a little bit of time to run. I'm not sure, because of course, as I was saying, the number of generators grows exponentially. So, but yeah. And then of course, the other question was when you find a deformation, you still have to show this the same one as the string theory. Right? So,
right.
And I mean, from what you are saying, I think what will happen is switching on this additional deformation, you cannot just reduce the ODD anymore. Yeah. So that means the transformation will probably not close. So you have to keep more. But of course, still you can reduce to OD, right, which is Lorentz, because OD always should be there and OD should always close. There is no reason why it actually should stop one step before the last step. And then of course the question is whether you still want to follow double field theory. Probably you won't, because it's still an extended field theory, but it's not doubling anymore on this model. Sorry guys, I don't want to. I feel bad because I already took enough of your time. Perhaps we can just continue to discuss that everybody wants to go.
Do you have some other questions? Oh, we can stop the recording.
Yes. Yes, I understand, and I understand.